Today we're going to take a very quick look at what an differential equation is. So to this point, you know how to solve lots of different types of equations, and I just have a few of the examples that are up here of equations that were being solved. So we could have polynomial equations where we use an awful lot of factoring to be able to solve for answers, rational equations where we have fractions, and we do end up doing a lot of polynomial work to be able to solve some of those, and even some trig equations where you are solving for an x value, but you tend to be solving, it represents some sort of angle measurement, and typically in radians. When we solve these equations, we typically come up with an x value at the very end, or multiple x values, as the cases would be here, for our solutions. And how we check those solutions is we can always go back to the original equation and plug those solutions back in to verify that they actually work and make a true statement. So we're going to be working with more equations, but they're going to be called differential equations. A differential equation has a rate of change, such as dy over dx, or maybe a y prime, or depending on the variables, you might end up with things like dv over dt or dA over dt, like we had in some related rates videos. And we have those equations in terms of x and y. The solutions, or the answers to these, would be the antiderivative for that particular dy over dx, or whatever rate term you have. So for example, we have a differential equation here that is x times y prime minus 3y equals 0. That can also be written as x times dy over dx minus 3y equals 0. The answer to this, the solution, would be some sort of function that when you plug in the derivative of the function and you also plug in the function itself, we would end up with a true statement. Similar to how in a regular equation, if we take the answer that we found and we go back and plug it in, we would come up with a true statement as well. The solution for this particular example is y is equal to x to the third. So I'm just going to verify that this is the solution for this differential equation. I'm going to find dy over dx, which would be 3x squared. And then I'm going to plug in the x to the third and the 3x squared in for the y and the dy over dx in the equation. I'm just going to sub those in. So x times 3x squared, take away a 3 times x to the third, and we're going to just verify that that's 0. So we end up with 3x to the third minus 3x to the third, which would be 0 equals 0. So that's an example of a differential equation and the solution that would happen to work for it. So we're going to be working with equations that have derivatives and other variables in them, almost like an implicit equation. And then the solutions are going to be the actual functions that they came from. So one of the other components you need to be able to do is to create differential equations out of context and being able to dissect the language to create the actual expression that is the differential equation that we're eventually going to solve. So we can take any written statement and we're going to translate it into that differential equation. And the two key phrases we're going to need to do that are the idea of a direct proportion and an inverse proportion. For a direct proportion, you have two amounts that are going to increase or decrease proportionally. And so we use some sort of constant, usually labeled with a k, to represent that relationship between how much one will increase as the other one increases. For an inverse relationship, where one of those amounts is getting larger while the other one is becoming smaller. So we're going to set up a fraction for this one with k over x, where k is that constant, to represent how, while one amount gets larger, the other amount is going to get smaller. So here's an example of a statement that we need to translate into a differential equation. So we're just going to start by reading this off. The rate of change of the volume of water in a pool with respect to time is directly proportional to the cube of its volume. So we're going to start off with a rate of change, and it's of the volume with respect to time. So it is a derivative that they're starting off with here, and we're going to call that dv over dt because it is the change of volume with respect to time. They then have the key phrase is directly proportional. So we know that this is a setup where we're going to have an equal to a constant times some sort of an amount. Something is equal to k times something else. And it's going to be directly proportional to the cube of its volume. So we're going to express that as v to the third. So we're going to have dv over dt is equal to k times v cubed. And that would become our differential equation that we will eventually solve. So for the rest of this, you want to take a look at the other statements that follow this and try to come up with what the differential equation would need to be for each of those situations.